For almost the entire history of our species, the edge of the universe was invisible, not because it wasn't there, because the universe itself refused to let us see it. Every star, every galaxy, every black hole you've ever heard about exists inside an invisible wall created by time itself. Beyond that wall lies light that has spent over 13 billion years racing across space. Light so ancient, it began its journey before Earth existed, before the sun ignited, before the Milky Way looked anything like it does today. For decades, astronomers believed that boundary had finally been reached. The Hubble Space Telescope had pushed deeper into the darkness than any machine in human history. It revealed galaxies forming only a few 100 million years after the Big Bang. It gave us what many believed was the earliest chapter of cosmic history. Most scientists thought there wasn't much left to find. After all, how much farther could anyone possibly look? Then James Webb opened its mirror. Everything changed. Almost immediately, Webb began detecting light that no telescope was ever supposed to see. Galaxies that appeared too large, too bright, too mature. Entire cosmic cities that seemed to exist before the universe had enough time to build them. It was as if archaeologists had dug into ancient soil expecting primitive stone tools, only to uncover a modern skyscraper. At first, astronomers assumed there had to be a mistake. Perhaps the distances were wrong. Perhaps the telescope had misidentified the objects. Perhaps the data needed recalibration. But observation after observation told the same story. The impossible objects remained, and the deeper Webb looked, the stranger the universe became. Some discoveries challenged our understanding of how galaxies grow. Others questioned how black holes formed. A few hinted that the earliest universe behaved in ways no computer simulation had ever predicted, and some still have no accepted explanation at all. Today, we're going to travel farther than any human has ever traveled. Not physically, but through light itself. We'll watch the first galaxies ignite, meet cosmic monsters that appeared impossibly early, explore structures so distant that their light began moving toward Earth before our own planet existed. And by the end, you may realize something unsettling. The edge of the universe wasn't the end of our search. It was the beginning of questions we never expected to ask. Because what James Webb found wasn't simply the oldest light in existence. It was evidence that the early universe may have been far stranger than anyone had imagined. But before Webb could rewrite the history of the cosmos, it first had to accomplish something that many engineers believed might never work. Part 1. The telescope that was never supposed to work. Before James Webb could discover impossible galaxies, before it challenged everything astronomers thought they knew, it first had to survive one of the most dangerous engineering gambles in human history. Because unlike Hubble, Webb was never designed to stay close to Earth. The moment its rocket engines shut down, there would be no rescue mission, no emergency repairs, no second chances. If even one of its thousands of moving parts failed, the most expensive scientific instrument ever built would become nothing more than another piece of space debris. It sounds almost unbelievable. But James Webb launched with more than 300 single points of failure. That means over 300 individual components had to work perfectly. Miss just one, and the mission could have ended before it ever began. Imagine building a machine the size of a tennis court, folding it into something small enough to fit inside a rocket, launching it over 1 million kilometers away, then asking it to unfold itself in the freezing vacuum of space, without a single human ever touching it. That wasn't science fiction. That was the plan. And for nearly 2 weeks after launch, millions of people watched something NASA engineers had nicknamed the 29 Days of Terror. Because every day, another critical deployment had to succeed. First, the solar array, then the communications antenna, then the momentum flaps, then the tennis court-sized sunshield. Each deployment depended entirely on the one before it, like knocking over dominoes, except every domino was worth billions of dollars. And then came the hardest part. The mirror. Webb's enormous primary mirror, measures more than 6.5 meters across, nearly 3 times larger than Hubble's. There was just one problem. No rocket on Earth could fit a mirror that large. So engineers did something nobody had ever attempted before. They folded it. 18 hexagonal mirrors, locked together like the petals of a mechanical flower, each one coated with an impossibly thin layer of gold. Not because gold looks beautiful, but because it reflects infrared light extraordinarily well. That gold coating is thinner than a human hair. In fact, if you melted all the gold covering Webb's mirrors into a single ball, it would barely fit inside your hand. Every mirror segment had to unfold perfectly. Then, using microscopic motors, move with an accuracy measured in nanometers. To appreciate how precise that is, imagine standing in New York and adjusting the height of a coin sitting in Los Angeles by less than the thickness of a human DNA strand. That's the level of precision Webb required before it could even take its first picture. Anything less, and the universe would appear hopelessly blurred. But even perfect mirrors wouldn't save the mission, because Webb wasn't built to observe visible light. It was built to see something our own eyes never can. Heat. Everything in the universe gives off infrared radiation. Stars, planets, dust clouds, even you. Right now, your body is glowing in infrared. You just can't see it. The earliest galaxies in existence are so unimaginably far away that their visible light has been stretched across billions of years of cosmic expansion. By the time that light reaches Earth, it isn't visible anymore. It has been stretched into infrared. To see the beginning of time, Webb had to become colder than almost anything naturally found on Earth. Its instruments operate near -233 degrees Celsius, only a few dozen degrees above absolute zero. If sunlight touched those instruments, their own heat would completely overwhelm the ancient signals arriving from the edge of the universe. That's why Webb carries one of the strangest objects ever sent into space. A 5-layer sunshield, roughly the size of a tennis court. Each layer is thinner than a sheet of paper. Together, they reduce the sun's heat by a factor of nearly 1 million. On one side of the telescope, temperatures can exceed 85 degrees Celsius. On the other side, they plunge below -230. Just a few meters apart, one side could boil water. The other could freeze almost every known gas. No telescope had ever attempted anything like it, and somehow, every deployment worked. Engineers waited nervously after each milestone. Another success. Then another. Then another. Against extraordinary odds, James Webb came alive. Months later, its mirrors locked into perfect alignment. The focus became razor-sharp. The instruments cooled, the cameras opened. For the first time, humanity possessed a machine capable of looking farther into time than ever before. And what it saw was almost too beautiful to believe. The first public image released by Webb appeared, at first glance, almost ordinary. A cluster of distant galaxies, floating in the darkness. But that image was hiding something extraordinary. Thousands of galaxies, some so distant, their light had travelled for over 13 billion years before reaching Webb's mirror. Every tiny red smudge represented billions of stars, entire civilizations of suns, compressed into pinpoints of light. Some of those galaxies no longer even exist. Their stars have exploded. Their shapes have changed. Some may have merged into even larger galaxies long before the dinosaurs walked the Earth. Webb wasn't seeing the universe as it is. It was seeing history. Every direction it looked became a different chapter in time. Nearby stars appeared almost present day. More distant galaxies became younger. Farther still, the first great structures of the cosmos emerged from darkness. Looking deeper into space was literally looking further into the past. For the first time, astronomers could begin watching the universe grow up. And almost immediately, something didn't make sense. The earliest galaxies weren't supposed to look mature. They should have been small, chaotic, dim, still struggling to assemble themselves from the leftover gas created by the Big Bang. Instead, many already looked surprisingly massive, almost finished. It was as if someone had opened a history book, turned to the very first chapter, and discovered fully grown cities standing where only scattered villages should have existed. At first, researchers wondered if they had made a mistake. Distance measurements can be difficult. Ancient galaxies can sometimes masquerade as closer ones. Extra observations were scheduled. Spectra were analyzed. Independent teams checked the data. The farther they looked, the worse the mystery became. The impossible galaxies refused to disappear. And if they were real, then one of the most successful theories in modern astronomy had just encountered its greatest challenge. But before we uncover what Webb actually found hiding in those first few 100 million years, take a second to look at how extraordinary this really is. Every discovery you're about to see comes from tiny packets of light that began their journey across space before Earth existed. If you're fascinated by the deepest mysteries of the universe, consider subscribing. There are billions of galaxies out there, and every week we're uncovering discoveries that make the cosmos even stranger than we imagined. You won't want to miss what's coming next. Because what Webb discovered inside those ancient red specks didn't simply surprise astronomers. It forced them to ask whether galaxies were somehow growing 10 times faster than the laws of physics seemed to allow. And that was only the beginning. Part 2. The galaxies that should not exist. The first images from James Webb weren't just beautiful. They were deeply unsettling. For decades, astronomers believed they understood how galaxies were born. The process seemed almost elegant. After the Big Bang, the universe was filled with enormous clouds of hydrogen and helium. Gravity slowly pulled those clouds together, forming the first stars. Those stars gathered into tiny galaxies. Over billions of years, those galaxies merged, growing larger and larger until they became the giant spiral and elliptical systems we see today. It was a slow process, orderly, predictable. At least, that's what every computer simulation suggested. According to our best models, the first few 100 million years of the universe should have been a cosmic construction site. Imagine flying over a city that's only just beginning to be built. You wouldn't expect skyscrapers. You'd expect scattered foundations, unfinished roads, and a handful of small buildings. The early universe should have looked exactly like that. Tiny galaxies, chaotic structures, weak starlight, nothing impressive. But when James Webb looked into that era, it found something entirely different. Some of the very first galaxies appeared astonishingly bright, not just slightly brighter, hundreds of times more luminous than astronomers expected. Even stranger, they looked surprisingly organized. Some already possessed smooth shapes and enormous stellar populations. They looked less like newborn galaxies, and more like systems that had already spent billions of years evolving. That should have been impossible, because there simply hadn't been enough time. Remember, the speed of galaxy growth isn't arbitrary. Stars don't appear overnight. Gravity has limits. Gas must cool. Clouds must collapse. Fusion must ignite. Then millions of stars must repeat the process over and over again before a galaxy reaches maturity. That takes time. A lot of it. Yet Webb kept finding galaxies that seemed to ignore that cosmic schedule entirely. One after another, they appeared where they shouldn't. At first, many astronomers suspected a simple explanation. Perhaps these galaxies only looked massive. Distance can be deceptive. A faint nearby object can sometimes masquerade as a bright distant one. The only way to know for certain was through spectroscopy. Every galaxy leaves behind a unique fingerprint. As light passes through gas, specific wavelengths are absorbed, creating tiny dark lines within the spectrum. Those lines reveal astonishing amounts of information: distance, chemical composition, temperature, motion, even the age of the stars inside. Unlike photographs, Spectra don't care about appearances. They're brutally honest. So astronomers pointed Webb's spectrographs toward these mysterious objects. One by one, the results arrived. And they made the mystery even worse. The galaxies really were that distant. Some existed just a few 100 million years after the Big Bang. There was no mistake, no calibration error, no optical illusion. The impossible galaxies were real. One of the most famous examples became known as Jade's GSZ 14-0. Its light began traveling toward Earth only about 290 million years after the Big Bang, making it one of the most distant confirmed galaxies ever observed. That number is difficult to appreciate. Imagine compressing the entire 13.8 billion year history of the universe into a single calendar year. On that scale, this galaxy already existed before the first week of January had ended. It shouldn't have had enough time to become what Webb observed, and yet, there it was. Even more surprising, Webb detected evidence of heavier elements inside galaxies from this incredibly early era. That may not sound extraordinary, but it changes everything. Immediately after the Big Bang, the universe was astonishingly simple. Almost all of its normal matter consisted of hydrogen and helium. The elements that make up planets, oceans, trees, your body, even the calcium in your bones, didn't exist yet. They had to be forged inside stars. When massive stars reach the end of their lives, they explode as supernovae, scattering newly created elements across space. Future generations of stars inherit those elements. Planets eventually form. Life becomes possible. It's a slow cycle of cosmic recycling. So when Webb began detecting galaxies that already contained measurable amounts of oxygen and other heavier elements, it implied something remarkable. Stars had not only formed incredibly early, they had already lived, died, and enriched their galaxies with new chemistry. Entire generations of stellar evolution had apparently unfolded in what cosmologically amounts to the blink of an eye. Astronomers were stunned, because every additional discovery pointed toward the same uncomfortable conclusion. The early universe wasn't developing gradually. It seemed to be growing up, almost immediately. Researchers began giving these systems an unforgettable nickname: universe breakers. Not because they literally break the universe, but because they threatened to break the models scientists had spent decades building. Computer simulations that once matched observations beautifully suddenly struggled to reproduce what Webb was seeing. Increase the rate of star formation? The galaxies still appeared too massive. Increase the amount of available gas? Still not enough. Allow stars to form more efficiently? Closer, but many observations remained difficult to explain. Every adjustment fixed one problem, while creating another. It was like trying to solve a puzzle where every new piece refused to fit. Some astronomers proposed that the first stars, known as Population 3 stars, may have been far more massive than anything we see today. If the earliest stars were hundreds of times the mass of our Sun, they would have burned through their fuel astonishingly quickly, producing enormous amounts of light before exploding and enriching the young universe with heavy elements. Others suggested that our understanding of dark matter, the invisible substance whose gravity helps shape galaxies, might be incomplete. Perhaps dark matter pulled gas together much faster during the universe's earliest moments than current models predict. Neither explanation has yet solved every mystery. And that's what makes Webb's discoveries so exciting. Not because they've overturned everything we know, but because they've revealed that there are chapters of cosmic history we still don't fully understand. Science advances when nature surprises us. And nature was delivering one surprise after another. Then Webb noticed something even stranger. Hidden among these ancient galaxies were tiny crimson objects unlike anything astronomers had ever seen before. At first, they looked insignificant, just faint red dots buried inside Webb's deep field images. Easy to overlook, easy to dismiss, but those tiny points of light would soon become one of the telescope's biggest mysteries. Some researchers believed they were galaxies. Others thought they were feeding black holes. A few wondered if they represented an entirely new class of cosmic object. Whatever they weren't behaving normally. And if these mysterious crimson lights were what scientists feared, then the early universe wasn't merely forming galaxies faster than expected, it was creating cosmic monsters long before they should have been possible. The deeper Webb looked, the more those tiny red dots began to rewrite the story of the first billion years of the universe. Part 3. The Little Red Dots. At first, almost nobody paid attention to them. They weren't spectacular. They weren't enormous spiral galaxies stretching across the screen. They weren't exploding stars or blazing quasars. They looked like tiny imperfections, just faint, reddish smudges buried deep inside Webb's images. Most were no larger than a few pixels. If you weren't looking for them, you'd probably scroll right past. But astronomy has a habit of hiding its biggest discoveries inside the smallest details, and these tiny red specks refused to behave. As researchers began cataloguing thousands of distant galaxies, they noticed an entirely new population of objects appearing over and over again. They shared the same deep crimson color, the same compact appearance, and something even stranger. They were far brighter than they had any right to be. Brightness matters, because in astronomy, light tells a story. A dim object usually means one of two things. It's either small or incredibly far away. These objects were almost certainly incredibly far away. Their intense red color revealed that immediately. As the universe expands, it stretches light itself. Blue wavelengths become green. Green becomes yellow. Yellow becomes red. Travel far enough, and even red light stretches into infrared. By measuring exactly how much that light has stretched, astronomers can estimate how far an object has traveled across cosmic history. The deeper the red, the farther back in time you're looking. These little red dots weren't just distant. Some appeared to exist less than 700 million years after the Big Bang. That alone would have made them fascinating. But distance wasn't the real mystery. Luminosity was. These tiny objects were pouring out astonishing amounts of energy, far too much for something their apparent size. Imagine seeing the light from a single apartment window, only to discover it was shining as brightly as an entire city. That's essentially what Webb was observing. Nobody expected objects this compact to be this powerful. Naturally, astronomers began searching for the obvious explanation. Maybe they weren't compact at all. Perhaps Webb simply couldn't resolve their true structure. After all, at these unimaginable distances, even enormous galaxies shrink into tiny points of light. Additional observations were scheduled, longer exposures, higher precision spectroscopy, different instruments. The results only deepened the mystery. Many of them remained incredibly compact. Some looked almost star-like, yet their spectra told a completely different story. They weren't individual stars. They were entire cosmic systems, but systems unlike anything astronomers had seen before. Soon, papers began appearing across the scientific community. Every team proposed a different explanation. Maybe these were galaxies undergoing unimaginably intense bursts of star formation, entire stellar populations igniting almost simultaneously. That could explain their incredible brightness. But there was a problem. To produce that much light, they would need to create hundreds, sometimes thousands, of new stars every single year. Our own Milky Way forms roughly 1 or 2 stars annually. These mysterious objects would have to outperform our galaxy by factors of hundreds, while existing when the universe itself was still practically an infant. That seemed unlikely. Another possibility quickly emerged. What if they weren't shining because of stars at all? What if something much darker was responsible? At the center of nearly every large galaxy lies a supermassive black hole. When gas falls toward one of these gravitational monsters, it doesn't disappear immediately. Instead, it spirals inward at incredible speeds. The friction becomes so intense that the gas heats to millions of degrees. Ironically, the darkest objects in existence become surrounded by some of the brightest light in the universe. From billions of light years away, that brilliant accretion disk can outshine every star inside its host galaxy. Could these little red dots simply be feeding black holes? The idea sounded promising, until astronomers calculated just how massive those black holes would need to be. Some estimates suggested millions, perhaps even billions, of solar masses. But once again, there wasn't enough time. Growing a black hole that large should require hundreds of millions, or even billions, of years. Yet Webb kept finding them astonishingly early in cosmic history. The universe seemed to have skipped several chapters. Then came another surprise. Several teams noticed that many of the little red dots simply vanished. Not physically, but when viewed at different wavelengths. Their appearance changed dramatically. Some seemed almost invisible in one instrument, yet blazed brilliantly in another. That behavior suggested thick clouds of gas and dust surrounding their central engines, almost like enormous cocoons, hiding whatever was happening inside. Imagine trying to identify a lighthouse while looking through dense fog. You know something incredibly bright is there. You just can't clearly see what's producing the light. That's exactly the problem astronomers faced. Every new observation answered one question, while creating two more. Were these galaxies? Were they quasars? Were they rapidly feeding black holes? Or were they something entirely new? Even today, the debate continues. Recent observations suggest that different little red dots may not all belong to the same category. Some likely are extremely compact galaxies, experiencing extraordinary bursts of star formation. Others appear to be powered by actively feeding supermassive black holes hidden behind thick veils of dust. In other words, the mystery may actually be several different mysteries disguised as one. But regardless of their true identities, they revealed something profound. The early universe was capable of producing complex structures far earlier than anyone had predicted. Whatever physical processes were operating during those first few 100 million years, they were astonishingly efficient, almost aggressive, as if the cosmos itself had been racing to build structure before anyone thought it could. The discovery forced theorists back to their simulations. Parameters were adjusted. Dark matter models were revisited. Star formation efficiencies were recalculated. Some simulations improved. Many still struggled. Nature, once again, was refusing to follow humanity's expectations. And yet, the little red dots were only a symptom of an even larger mystery. Because hidden behind several of those crimson objects, Webb found evidence for something even harder to explain. Not galaxies, not stars, but enormous black holes, already weighing millions of suns. At a time when the first generations of stars had barely begun to shine. The question wasn't simply how they grew so quickly. The question was far more unsettling. Did some of these cosmic monsters exist before galaxies themselves had fully formed? Part 4. The black holes that were there too soon. Before the first great galaxies filled the universe with light, something else may already have been waiting in the darkness. Invisible, hungry, growing. For decades, astronomers believed they understood how black holes were born. The process seemed straightforward. A massive star spends millions of years fusing hydrogen into heavier elements. Eventually, it runs out of fuel. Without the outward pressure from nuclear fusion, gravity wins. The star collapses. If it's massive enough, it leaves behind a black hole. Simple, elegant, and supported by countless observations. But that explanation comes with one unavoidable limitation: time. Even the biggest stars don't die overnight. They need millions of years before gravity can crush them into black holes. Then those black holes must slowly feed. Gas falls inward. Stars drift too close. Galaxies merge. Little by little, they grow larger. That's how astronomers believed the universe created the supermassive black holes sitting inside nearly every galaxy today. Slowly, patiently, over billions of years, James Webb wasn't supposed to find them at the very beginning, but that's exactly what happened. As astronomers examined some of Webb's most distant observations, they noticed unusually bright cores hiding inside several young galaxies. The light wasn't coming from stars, it was concentrated, intense, almost laser-like, exactly what you'd expect from matter falling into an actively feeding black hole. One object in particular captured everyone's attention. Its light had traveled for more than 13 billion years before reaching Earth. When we observe it today, we're seeing it less than 600 million years after the Big Bang. Yet evidence suggested it already contained a black hole weighing millions of times the mass of our Sun. Pause for a moment and think about what that means. If the universe were a single human lifetime, this black hole would have reached adulthood before most stars had even been born. Something didn't add up. Because growing a black hole isn't easy. People often imagine black holes as cosmic vacuum cleaners, sucking in everything around them. Reality is far stranger. Black holes are actually surprisingly inefficient eaters. As gas spirals inward, it heats to extraordinary temperatures. That hot gas produces intense radiation. Eventually, that radiation pushes back against incoming material. It's almost like a campfire. Add a little wood, the fire grows. Throw on too much at once, and the heat begins pushing smoke and burning air back toward you. Black holes face a similar limit. Astronomers call it the Eddington limit. It's essentially nature's speed limit for black hole growth. Feed too quickly, and the radiation begins blowing material away faster than it can fall inward. According to decades of physics, even feeding continuously at this maximum rate, many of Webb's early black holes shouldn't exist yet. There simply wasn't enough time, and yet, there they were. Some researchers wondered if the initial seeds were much larger than anyone had imagined. Perhaps instead of beginning as stellar black holes weighing 10 or 20 suns, the first black holes formed weighing hundreds of thousands of solar masses. That would certainly solve the timing problem, but it created another question. Where would such enormous seeds come from? One possibility is known as direct collapse. Imagine an enormous cloud of primordial hydrogen. Not a star, not a galaxy, just a gigantic cloud of gas. If the conditions are exactly right, gravity may overwhelm the cloud before individual stars ever have a chance to form. Instead of producing thousands of stars, the entire cloud collapses almost at once, straight into a black hole. No supernova, no stellar evolution, just gravity, taking a shortcut. It's one of the most fascinating ideas in modern cosmology, and Webb is providing some of the strongest evidence yet that something like this may have happened. But even direct collapse doesn't explain every observation. Some black holes still appear too massive, too active, too early. The deeper Webb looked, the stranger they became. Then astronomers found something even more unsettling. Several of these ancient black holes appeared to outweigh the galaxies surrounding them. Normally, a galaxy and its central black hole grow together. The galaxy builds stars. The black hole feeds. Over billions of years, they influence one another like dance partners. Neither one races too far ahead, but Webb revealed systems where the black hole seemed almost premature, as though the monster had arrived first, and the galaxy was still struggling to catch up. Imagine discovering a fully grown skyscraper standing in the middle of an empty field, while the surrounding city was still laying its first roads. That's essentially what astronomers were seeing. It forced researchers to consider an extraordinary possibility. What if black holes didn't simply grow inside galaxies? What if, in some cases, they actually helped create them? Modern galaxies don't exist in isolation. Their stars orbit enormous concentrations of dark matter, the invisible substance making up roughly 85% of all matter in the universe. Dark matter provides the gravitational framework. Gas falls into that framework. Stars ignite. Galaxies emerge. But perhaps, under the extreme conditions of the early universe, rapidly growing black holes also shaped that process. Their immense gravity could have accelerated the collapse of surrounding gas, helping galaxies assemble faster than expected. If true, then the relationship between galaxies and black holes isn't what we thought. The black hole wouldn't simply be a passenger, it would be one of the architects. An idea once considered speculative is now being taken increasingly seriously because of Webb's observations. And the surprises didn't stop there. Some of these early black holes weren't quietly feeding. They were erupting. As matter spiraled inward, it released extraordinary amounts of energy. Jets of plasma blasted into intergalactic space at nearly the speed of light. These jets stretched for thousands of light years, heating surrounding gas, triggering star formation in some regions, while suppressing it in others. The universe's earliest monsters weren't passive objects. They were reshaping their surroundings, changing the evolution of entire galaxies, all within the universe's first few 100 million years. It's astonishing to think about. Long before Earth, before the Sun, before our own galaxy looked anything like it does today, these cosmic giants were already transforming the young universe. But just as astronomers were beginning to piece together this story, Webb uncovered another mystery. One that didn't involve black holes at all. It involved something far more fundamental, the universe itself. Because hidden within the oldest light ever observed was evidence that the first generations of stars may have lived and died far earlier than anyone thought possible. And without those stars, none of these impossible galaxies or impossible black holes should have existed at all. To understand how Webb may have rewritten the birth of the first stars, we have to travel even closer to the beginning of time itself. Part 5. The first stars may have lived and died before they were supposed to. Long before planets, before galaxies resembled anything we recognize today, the universe was an incredibly dark place. For nearly 400 million years after the Big Bang, there were no stars, no galaxies, no planets, no sunlight, just an endless ocean of hydrogen, helium, and darkness. Astronomers call this period the Cosmic Dark Ages. It wasn't dark because something blocked the light. There simply wasn't any. Imagine standing alone in an endless desert on the darkest night imaginable. No moon, no stars, no distant cities. Now remove the earth beneath your feet. Remove the sky. Remove the air. That's closer to what the young universe looked like. Everything we know, every galaxy, every nebula, every planet, every atom inside your body was still waiting to be built. Gravity had only just begun its slow work. Tiny fluctuations left behind by the Big Bang acted like invisible fingerprints. Some regions contained slightly more matter than others. Not much. Just enough. Over millions of years, gravity quietly amplified those tiny differences. Matter drifted together. Clouds became denser. The denser they became, the stronger gravity became. And the stronger gravity became, the faster those clouds collapsed. Eventually, some of those collapsing clouds reached extraordinary temperatures. Hydrogen nuclei slammed together with incredible force. Nuclear fusion ignited. For the very first time, the universe produced starlight. Astronomers believe these first stars were unlike anything alive today. They weren't merely larger than our sun. Some may have been 100, 200, perhaps even 300 times more massive. To understand how enormous that is, imagine replacing our sun with a star hundreds of times heavier. Its brightness would be almost unimaginable. Its radiation would sterilize everything nearby. Its lifetime would be astonishingly short. Large stars burn through their fuel at unbelievable speeds. A star twice the sun's mass doesn't live half as long. It lives far less. The bigger the star, the faster it dies. Some of the universe's first stars may have lived only a few million years before exploding. On cosmic timescales, that's almost instantaneous. Those explosions were unlike anything happening today. Modern supernovae are already among the most energetic events in existence, but some of the earliest stars may have ended their lives in even more violent explosions, called pair instability supernovae. Instead of leaving behind neutron stars or black holes, these colossal explosions may have completely destroyed the star itself. Nothing remained. Every atom forged inside that star, oxygen, carbon, silicon, magnesium, was blasted into interstellar space. Those explosions transformed the universe forever, because before the first stars died, the cosmos was chemically simple. Afterward, everything changed. The raw ingredients for rocky planets, oceans, mountains, and eventually life began spreading across space. For decades, astronomers believed this entire process unfolded slowly. One generation of stars, then another, gradually enriching the universe over hundreds of millions of years. It seemed perfectly reasonable, until James Webb arrived. As Webb studied some of the oldest galaxies ever observed, its spectrographs detected something deeply unexpected. Many already contained surprisingly large amounts of heavier elements. Not enormous quantities, but enough to create a serious problem, because those elements shouldn't have existed yet. Remember, every atom heavier than helium has to be manufactured inside stars. Stars need time to form, time to live, time to explode. Then entirely new stars must form from that enriched material. It's a cosmic recycling program, and recycling takes time. Yet Webb kept finding galaxies whose chemical fingerprints suggested that several generations of stars had already come and gone. It's almost like walking into a forest, finding giant oak trees, and realizing they've already dropped seeds, grown saplings, and produced a second forest, all within a single summer. The timeline simply didn't seem to work. Something had accelerated the universe's earliest evolution. The question was, what? One possibility immediately gained attention. Maybe those first stars were even larger than anyone imagined. Instead of 100 solar masses, perhaps some reached several hundred. That would allow them to burn through their nuclear fuel astonishingly quickly. Their brief lives would flood the young universe with heavy elements almost immediately. It's an elegant idea, but there's a catch. No one has ever directly observed one of these first-generation stars. Not one. Astronomers call them population 3 stars. Ironically, they were probably among the brightest stars ever to exist, yet they remain completely invisible to us. Why? Because they died too quickly. By the time enough light reached Earth for modern telescopes to observe, they were already gone. James Webb has likely missed them by hundreds of millions of years. Instead, it sees only their fingerprints, the chemical evidence they left behind. It's like investigating an ancient civilization that vanished thousands of years ago. The people are gone, the cities have crumbled, but scattered across the landscape, their tools, their buildings, their monuments, still tell their story. Webb is performing cosmic archaeology. Every spectrum it records, every galaxy it analyzes, contains clues left behind by stars that disappeared over 13 billion years ago. And those clues keep pointing toward the same conclusion. The first stars may have lived much faster, burned much hotter, and died much earlier than astronomers expected. If that's true, then the universe didn't spend hundreds of millions of years slowly waking up. It exploded into complexity. Almost immediately, entire galaxies, black holes, chemical elements, all appearing with astonishing speed. The orderly picture of cosmic evolution was beginning to look far less orderly. But just when astronomers thought the first stars explained everything, Webb uncovered something that threatened the idea all over again, because some of the oldest galaxies weren't merely rich in heavy elements, they were producing stars at rates so extreme they bordered on the impossible. Imagine a factory designed to build 2 cars every year. Now imagine walking inside and discovering it's somehow producing 1,000 cars every single day. That's the scale of the mystery. Some ancient galaxies appeared to be creating hundreds, sometimes even thousands, of new stars every year, enough to rival galaxies that had spent billions of years growing. How could that happen? When the universe itself had barely celebrated its first birthday, the answer may lie hidden inside something we still can't see, something that outweighs every star, every planet, and every galaxy combined. Something so mysterious that even today, scientists still don't know exactly what it's made of: dark matter. And what James Webb is revealing about it may be even stranger than the impossible galaxies that started this journey. Part 6. The invisible scaffold holding the universe together. You can't see it. You can't touch it. No telescope has ever photographed it. And yet, without it, none of the galaxies James Webb has discovered should exist. Everything you've seen so far, the impossible galaxies, the ancient black holes, the earliest stars, may all trace back to something humanity has never directly observed: dark matter. If you could somehow fly beyond the Milky Way, far enough to look back at our galaxy from the outside, you'd notice something strange. The hundreds of billions of stars inside our galaxy orbit its center at astonishing speeds. Too fast, much too fast. According to Newton's laws, many of those stars should have escaped billions of years ago. Imagine tying a ball to the end of a string. Spin it fast enough, and the string snaps. The ball flies away. The Milky Way should behave the same way. Its outer stars move so quickly that the visible matter inside the galaxy simply doesn't provide enough gravity to keep them bound. Yet, they stay exactly where they are. Something else, something completely invisible, is holding everything together. Astronomers first realized this in the 1930s. At first, they assumed the calculations were wrong. Perhaps galaxies contained more faint stars than anyone realized. Maybe giant clouds of cold gas were hiding between them. But decade after decade, the evidence became impossible to ignore. Every galaxy cluster, every large structure in the universe behaved as though enormous amounts of invisible matter surrounded them. Today, scientists estimate that everything you've ever seen, every planet, every nebula, every black hole, every human being, accounts for only about 15% of all the matter in the universe. The remaining 85% appears to be something else entirely. We call it dark matter. Not because it's black, not because it's evil, simply because it doesn't interact with light. Light passes through it. Infrared passes through it. Radio waves pass through it. It neither emits, nor reflects, nor absorbs electromagnetic radiation in any detectable way. To every telescope humanity has ever built, dark matter is completely invisible. The only reason we know it's there is because gravity refuses to lie. Every time astronomers calculate how galaxies should move, they get the wrong answer, unless they include an enormous halo of invisible mass surrounding them. It's like walking into an empty room, seeing footprints appear across the floor, chairs sliding by themselves, doors opening without anyone touching them, and realizing something invisible is standing right beside you. You can't see it, but its effects are everywhere. For decades, dark matter remained one of astronomy's greatest mysteries. Then James Webb arrived. Not because Webb could finally photograph dark matter. It couldn't. No telescope can. Instead, Webb began revealing something almost as extraordinary. It started showing us what dark matter was doing. Imagine building a city. Before construction begins, workers first erect an enormous framework, steel beams, Support columns, foundations. The buildings don't appear out of nowhere. They grow around that hidden structure. Many cosmologists now believe the universe formed the same way. Shortly after the Big Bang, dark matter began clumping together under its own gravity. Unlike ordinary matter, it wasn't slowed by radiation. It didn't need to cool. It simply gathered into enormous invisible halos. Those halos became the universe's framework, the scaffolding. Later, ordinary gas drifted into those gravitational wells. Stars ignited. Galaxies formed. Without dark matter, there would have been nowhere for those first galaxies to assemble. This idea had been around for decades, but Webb's observations suddenly made it far more difficult to ignore. Remember those impossible galaxies from the previous chapter? Some researchers now suspect that dark matter in the early universe may have behaved differently than current simulations predict. Perhaps it clumped together faster. Perhaps its distribution wasn't as smooth as we assumed. Or perhaps our understanding of dark matter itself is incomplete, because the numbers still refuse to cooperate. Even when scientists include dark matter in their simulations, many still struggle to reproduce the gigantic galaxies Webb keeps finding less than 1 billion years after the Big Bang. Something is still missing, and that missing piece may be hiding inside dark matter itself. No one knows what dark matter actually is. That's not an exaggeration. After nearly a century of research, it's still one of the biggest unanswered questions in physics. Some researchers believe it's made of entirely new particles that have never been detected on Earth. Others propose ultralight quantum fields stretching across entire galaxies. Some have suggested invisible primordial black holes. Others think gravity itself may behave differently across cosmic distances. Every possibility sounds extraordinary, because every ordinary explanation has failed. Yet Webb keeps adding pressure to the mystery. The telescope has observed gravitational lenses with unprecedented detail. Massive galaxy clusters bending light from objects billions of light years behind them. These natural cosmic magnifying glasses allow astronomers to map where invisible mass must be hiding. The results are astonishing. Sometimes, dark matter appears almost perfectly smooth. Other times, it seems clumpy, chaotic, uneven, like invisible mountains and valleys scattered throughout space. Those subtle differences matter, because wherever dark matter gathers, galaxies eventually follow. It's almost like watching leaves floating on a river. You can't see the current beneath the surface, but by watching the leaves, you can map the invisible flow of the water. Webb is doing exactly that, except the river spans billions of light years, and the leaves are entire galaxies. The more Webb maps these distant structures, the more it appears that dark matter shaped the universe long before the first stars illuminated it. In many ways, the visible universe may simply be decoration. The real architecture, the invisible skeleton, was already there. But just when astronomers thought dark matter might explain Webb's impossible discoveries, another observation complicated the picture. Because some galaxies weren't merely growing too quickly, they were growing without enough raw material. Imagine walking into a bakery capable of producing 10 loaves of bread every hour, only to find hundreds stacked on the shelves. You search the kitchen. There's barely any flour, no extra ovens, no hidden workers. Nothing explains the production. That's exactly what Webb began finding. Ancient galaxies packed with stars, despite appearing to lack enough ordinary matter to build them. The universe wasn't just assembling galaxies faster than expected. It seemed to be creating them with impossible efficiency. Somehow, the earliest cosmos had become an extraordinarily productive factory, a factory that modern physics still struggles to explain. And if galaxies weren't the biggest surprise hiding inside Webb's deepest images, what came next certainly was. Because buried among those ancient structures, Webb found evidence of something so distant that its light had begun its journey when the universe was less than 300 million years old, a galaxy so ancient that simply confirming its existence forced astronomers to redraw the timeline of cosmic history. The farther Webb looked toward the beginning of time, the more the beginning itself seemed to move. Part 7. The oldest galaxy ever confirmed. For decades, astronomers thought they knew where the beginning was. Not the beginning of the universe, the beginning of galaxies. Every telescope before James Webb had slowly pushed that boundary farther away. Each new generation looked a little deeper into space, and therefore, a little further back in time. Hubble spent years staring at what appeared to be an empty patch of sky. It was one of the boldest scientific experiments ever attempted. Imagine holding a drinking straw at arm's length and looking through it toward the night sky. The tiny circle you see contains thousands of stars. Now imagine choosing one of the darkest places inside that tiny circle, where almost nothing appears to exist, and pointing your telescope there for days. That's essentially what Hubble did. When the image was finally assembled, astronomers were stunned. The darkness wasn't empty. It was overflowing. Thousands of galaxies filled that tiny region alone. Every one of them, a city containing billions of stars. For years, those images represented humanity's deepest look into the universe. Many believed we were approaching the limit of what was physically possible. Then, James Webb repeated the experiment. Everything changed. Where Hubble saw darkness, Webb saw structure. Where Hubble detected faint smudges, Webb revealed entire galaxies. Its enormous mirror and infrared vision allowed it to collect ancient light that had been stretched beyond Hubble's reach. Suddenly, the edge of observable history moved even farther away. One by one, candidate galaxies appeared at distances nobody expected. Each one had to be verified, because appearances can be deceiving. An ordinary nearby galaxy covered in dust can sometimes imitate an extremely distant one. Astronomers have learned to be skeptical. Extraordinary claims require extraordinary evidence. That's why every promising candidate undergoes the same rigorous process. Photographs alone aren't enough. Researchers use spectroscopy. Instead of simply asking, "What does it look like?" they ask, "What does its light actually say?" Light behaves almost like a barcode. Every chemical element absorbs specific wavelengths. Hydrogen leaves one pattern, oxygen another, carbon another. When astronomers spread a galaxy's light into a spectrum, those fingerprints appear. Even more importantly, they reveal something called redshift. The farther a galaxy lies from Earth, the more the expansion of the universe stretches its light. Measuring that stretching allows astronomers to calculate how long the light has been traveling. It's one of the most powerful tools in modern astronomy. And when Webb examined one particular object, the numbers were almost unbelievable. The galaxy known as Jade's GS Z14-0 wasn't just distant. It was confirmed to have existed roughly 290 million years after the Big Bang. To appreciate how extraordinary that is, imagine compressing the entire age of the universe into a single 24-hour day. On that scale, this galaxy would already exist just after midnight. Everything that came afterward, the Milky Way, the Sun, the Earth, dinosaurs, human civilization, would all unfold during the remaining 23 hours and 50 minutes. Yet somehow, this galaxy was already there, and it wasn't alone. Webb kept finding others from the same era. Each confirmation pushed astronomers into uncomfortable territory, because galaxies this early weren't supposed to be this bright. Brightness usually means stars. Lots of them. Billions of them. But building billions of stars requires enormous reservoirs of gas, efficient star formation, and time. Three things the young universe wasn't supposed to possess in abundance. At least, according to previous models. The discovery forced scientists to revisit one of cosmology's oldest assumptions. Perhaps galaxies don't always grow slowly. Maybe, Under the extraordinary conditions of the early universe, they could assemble at breathtaking speed. Imagine watching a snowstorm. Normally, flakes accumulate gradually. A thin layer, then a thicker one. Eventually, the ground disappears beneath the snow. Now imagine looking outside and finding 10 feet of snow had appeared almost instantly. You'd immediately assume something unusual had happened. That's exactly how astronomers felt. The universe seemed to have skipped its slow beginning. Instead of tiny protogalaxies cautiously forming their first stars, Webb was finding mature systems that appeared to have raced through millions of years of evolution almost overnight. Naturally, not everyone agreed. Some researchers argued that astronomers were overestimating the masses of these galaxies. Perhaps they weren't as enormous as early calculations suggested. Others proposed that intense bursts of star formation could temporarily make relatively small galaxies appear much brighter than they actually were. Both ideas remain under active investigation. And that's one of the most exciting parts of this story. James Webb isn't proving every old theory wrong. It's revealing where our theories need to improve. That's how science moves forward. Not by refusing surprises, but by following the evidence wherever it leads. Then, another discovery quietly slipped into the data. At first, almost nobody noticed it. While studying the spectra of these record-breaking galaxies, astronomers found something hiding inside their light. Oxygen. Not just traces, clear evidence that at least some of these galaxies had already been enriched by earlier generations of stars. That single observation carried enormous implications. Because oxygen doesn't exist naturally after the Big Bang. It has to be forged inside stars through nuclear fusion. Those stars must then explode, scattering oxygen into surrounding gas. Only afterward can new stars inherit that material. In other words, finding oxygen meant these galaxies already had a history. They weren't witnessing the birth of the first stars. They were seeing what came after. Somewhere, even earlier, an even older generation of stars had already lived and died. It's a bit like excavating an ancient city and discovering paved roads. Roads imply carts. Carts imply trade. Trade implies settlements that existed even earlier. One discovery suddenly points toward an entire chapter of history you haven't uncovered yet. That's exactly what Webb did. Instead of showing us the beginning, it hinted that the real beginning might lie even farther back. And that realization sparked one of the biggest races in modern astronomy. If galaxies already looked this mature only 290 million years after the Big Bang, what existed before them? Could Webb detect light from even earlier structures? Could it catch the first stars themselves? Or could there be objects hiding in the darkness that no one had ever imagined? The deeper astronomers searched, the stranger the answers became. Because among Webb's oldest observations, they found galaxies producing stars at rates so extreme, they appeared to be transforming entire oceans of gas into starlight almost overnight. Some researchers began calling them cosmic star factories, and if their calculations were correct, these ancient systems weren't just growing quickly, they were growing faster than the universe itself seemed ready for. What Webb found next wasn't simply another distant galaxy. It was evidence that the early universe may have been the most productive era in the entire history of the cosmos. Part 8. The Cosmic Star Factories. Imagine standing inside the largest factory ever built. Conveyor belts stretch beyond the horizon. Machines never stop moving. Raw materials pour in from every direction. Every second, something new is being created. Now imagine that factory isn't building cars, or computers, or airplanes. It's building stars, entire suns, every few hours. That sounds impossible. But according to James Webb, some of the earliest galaxies in the universe were operating at production rates that almost defy belief. For most of cosmic history, star formation has been a relatively patient process. A cloud of gas slowly cools. Gravity begins pulling it inward, The cloud fragments into smaller pockets. Those pockets collapse. Temperatures climb. Eventually, nuclear fusion ignites. A new star is born. From beginning to end, the process can take millions of years. Our own Milky Way follows that rhythm today. On average, it creates only 1 or 2 new stars each year. Considering the galaxy contains hundreds of billions of stars, that pace may seem surprisingly slow, but it's exactly what astronomers expect. Gas is precious. Gravity takes time. Nature doesn't rush. At least, that's what we believed. Then Webb began measuring star formation inside some of the oldest galaxies ever discovered. The numbers didn't just exceed expectations, they shattered them. Some galaxies appeared capable of producing hundreds of new stars every single year. Others may have been creating even more. Not for a few weeks, not for a few months, potentially for millions of years. Picture 2 bakeries. The first carefully bakes 1 loaf of bread every day. The second somehow produces an entire city's supply before breakfast. That's the scale of the difference. These weren't ordinary galaxies. They were cosmic manufacturing plants. Entire stellar populations were appearing at astonishing speed. Naturally, astronomers asked the obvious question: where was all the fuel coming from? Stars don't simply appear. Every new sun requires enormous quantities of hydrogen gas. Build enough stars, and eventually the galaxy should begin running out of material. Yet many of Webb's galaxies showed little sign of slowing down. Instead, they appeared to be feeding continuously, almost as though invisible rivers of gas were pouring into them from every direction. Computer simulations had actually predicted something similar years before Webb launched. On the largest scales, the universe resembles an enormous web. Not a spider's web, a cosmic one. Gigantic filaments of gas and dark matter stretch across hundreds of millions of light years. Where several of these filaments intersect, galaxies tend to form. Think of it like rivers flowing toward a lake. As long as the rivers keep delivering water, the lake never empties. Some astronomers now believe these ancient galaxies sat at the intersections of multiple cosmic filaments. Instead of slowly collecting gas from nearby space, they may have been connected to vast intergalactic highways, continuously delivering fresh fuel. If that's true, the first galaxies weren't isolated islands. They were connected, fed by an invisible network spanning the young universe. James Webb can't directly photograph those streams. They're far too faint, but it can observe their consequences: the incredible rate of star formation, the unusual chemistry, the unexpectedly large masses. Each clue points toward the same possibility. The earliest galaxies may have had access to far more fuel than anyone imagined, but fuel alone doesn't explain everything. Imagine giving 2 builders the same stack of bricks. One finishes a small house. The other somehow constructs a skyscraper before sunset. Clearly, something about the second builder is different. The same appears to be true for these ancient galaxies. Not only did they possess enormous amounts of gas, they transformed that gas into stars with astonishing efficiency. Some researchers suspect the extreme conditions of the early universe made star formation fundamentally different. Back then, the universe was much denser than it is today. Galaxies sat closer together. Gas clouds collided more often. Gravity had an easier time pulling matter into compact regions. Everything happened inside a universe that was younger, hotter, and far more crowded. Imagine trying to build snowballs during a gentle winter snowfall. Now compare that to standing in the middle of an avalanche. Both involve snow, but one environment is dramatically more efficient. Perhaps the early universe functioned the same way. The raw ingredients weren't necessarily different. The environment was. And that environment may have accelerated nearly every process taking place. Yet even that explanation leaves behind another puzzle. Because several of Webb's star factories appear remarkably calm. If you've ever seen images of nearby starburst galaxies, they're chaotic, violent, twisted by explosions, Powerful stellar winds blast gas in every direction. Massive stars flood space with intense ultraviolet radiation. It's messy. The earliest galaxies, at least some of them, don't always look that way. Despite creating stars at extraordinary rates, many appear surprisingly compact, surprisingly organized, almost disciplined. It's as though the universe somehow found a way to mass-produce stars without descending completely into chaos. No one knows exactly how, and that's becoming a recurring theme. Almost every time Webb pushes deeper into the universe, nature answers one question by asking three more. Then came another surprise. Some of these ancient star factories weren't merely producing stars. They were producing stars with unexpected chemical fingerprints, using Webb's infrared spectrographs. Astronomers detected signatures suggesting that the gas inside certain galaxies had already been enriched by multiple generations of stellar explosions. That shouldn't happen so quickly. Remember, heavy elements like oxygen, carbon, and nitrogen have to be manufactured inside stars. Each generation enriches the next. Finding these elements in galaxies this early means the cycle of birth, death, and rebirth had already repeated itself several times. It's almost as if the universe hit the fast-forward button during its first few 100 million years. Every observation pointed toward astonishing efficiency. Stars formed earlier. Galaxies assembled faster. Black holes grew larger. Chemistry evolved more quickly. The universe wasn't simply waking up, it was racing. But hidden among these remarkable galaxies, Webb found something even more extraordinary. Some weren't just forming stars. They were hiding monsters at their centers. Objects so luminous, they briefly outshone every star around them combined. Not because the stars were dim, because something else was consuming matter at an almost unimaginable rate. These were not ordinary black holes. They belonged to one of the most violent classes of objects in the entire universe. Quasars. And what Webb discovered about the earliest quasars may completely change our understanding of how the first cosmic giants came to dominate the young universe. Because if the galaxies were astonishing, the monsters hiding inside them were even harder to explain. Part 9. The cosmic beacons that shouldn't have existed. Long before our sun was born, before the Milky Way settled into the graceful spiral we see today, before Earth even existed, the universe was already producing objects so bright they could outshine entire galaxies. Not stars, not supernovas, something far stranger. Quasars. If black holes are the universe's greatest predators, then quasars are what happens when those predators feed without restraint. Most people imagine black holes as perfectly black spheres silently swallowing everything nearby. Reality is almost the exact opposite. A black hole itself emits no light, but the material falling toward it can become the brightest thing in the universe. Imagine pouring water down a drain. As the water spirals inward, it speeds up. Now replace that water with enormous clouds of gas. Replace the drain with a black hole containing millions, or even billions, of times the sun's mass. The gas doesn't fall straight in. It spirals. Faster. Hotter. Faster still. Eventually, friction heats that gas to temperatures exceeding millions of degrees. It begins glowing. First in visible light, then ultraviolet, then X-rays. The black hole remains invisible, but everything around it becomes a furnace brighter than billions of stars. That's a quasar. For decades, astronomers believed quasars represented one of the final stages of galactic evolution. Large galaxy, large black hole, billions of years of feeding. Eventually, a brilliant quasar appears. It made perfect sense, until James Webb looked back toward the beginning of time. Instead of finding only young galaxies, Webb found galaxies whose central black holes were already feeding furiously. Some existed less than 1 billion years after the Big Bang. That immediately raised an uncomfortable question. How did they get so big, so quickly? Because growing a supermassive black hole is astonishingly difficult. Imagine trying to fill an ocean using a garden hose, even if you never stopped. It would take an unimaginably long time. That's essentially the problem astronomers faced. According to standard models, many early black holes simply didn't have enough time to reach the enormous masses required to power quasars. Yet Webb kept finding them, one after another. Each observation pushed the timeline further back. Each discovery forced scientists to rethink how quickly these cosmic giants could grow. Then something even stranger emerged. When astronomers compared the masses of several early quasars to the galaxies surrounding them, the numbers didn't match expectations. Normally, a galaxy outweighs its central black hole by an enormous margin. The galaxy grows, the black hole grows alongside it, like two dancers moving together. But some of Webb's earliest quasars seemed almost out of balance. Their black holes appeared disproportionately massive, almost as though they had grown faster than the galaxies themselves. It's a little like finding the engine of a skyscraper-sized ship before anyone has finished building the ship around it. Something seemed backwards. One possible explanation involves the violent conditions of the early universe. Back then, galaxies collided far more frequently than they do today. When galaxies merge, vast reservoirs of gas are thrown toward their centers. That gas becomes food, and hungry black holes don't waste opportunities. Imagine opening a dam. Water rushes forward instantly. Something similar happens during galactic mergers. Huge amounts of gas suddenly lose their stable orbits. Gravity takes over. The gas plunges toward the central black hole. For a brief period, the black hole enters a feeding frenzy. Its brightness increases dramatically. A quasar is born. Webb has revealed that these events may have been far more common in the universe's youth than anyone previously imagined. The first billion years may have been filled with galaxies crashing together, feeding black holes, and reshaping one another at extraordinary speed. But mergers alone don't explain every observation. Some early quasars appear to exist inside surprisingly compact galaxies. Others don't show clear evidence of recent collisions. Again, nature refuses to give us one simple answer. Instead, every new discovery adds another layer to the mystery. Then Webb began studying the gas surrounding these ancient quasars. What it found surprised researchers yet again. Instead of quietly falling inward, some of that gas was being blasted back into space. Powerful winds, traveling at thousands of kilometers per second, were erupting from the regions around the black holes. Imagine standing near a hurricane. Now imagine the wind traveling not at 200 kilometers per hour, but several thousand, powerful enough to sweep entire clouds of gas out of a galaxy. That's what some quasars appear to be doing. Ironically, the same black hole helping build a galaxy may also be shutting parts of it down. As the quasar brightens, its radiation becomes so intense that it heats surrounding gas. Hot gas struggles to collapse. Without collapsing gas, new stars cannot form. In other words, the brightest objects in the universe may actually prevent future stars from being born. It's one of the strangest balancing acts in cosmology. Black holes can both create the conditions that help galaxies evolve and later suppress the very star formation those galaxies depend on. Creation and destruction driven by the same object. James Webb is allowing astronomers to watch that relationship unfold at earlier times than ever before. And every observation is forcing theorists to refine their models. Not abandon them, refine them. That's an important distinction. Webb isn't proving that everything we knew was wrong. It's revealing that the early universe was more dynamic, more efficient, and more complex than previous observations could show. Then, while astronomers were celebrating these remarkable discoveries, Webb captured something even more astonishing. Not a galaxy, not a quasar, but an image so deep that almost every point of light inside it represented an entire galaxy, thousands upon thousands of them, some closer, some farther, some whose light began traveling toward us more than 13 billion years ago. It wasn't just another beautiful picture. It became one of humanity's greatest time machines, because hidden inside that single image were snapshots of the universe at hundreds of different ages, all visible at once. And among those countless galaxies, gravity itself was performing a trick that Albert Einstein predicted over a century ago. A trick so powerful, it allowed James Webb to see objects that would otherwise have remained forever invisible. The universe itself had become a telescope. Part 10. The universe became a telescope. Sometimes, the greatest discoveries in astronomy don't come from building a bigger telescope. Sometimes, the universe does the work for us. More than 100 years ago, Albert Einstein made a prediction that sounded almost impossible. According to his theory of general relativity, gravity doesn't simply pull on objects. It bends space itself. Imagine placing a bowling ball onto the center of a stretched rubber sheet. The sheet sinks. Now roll a marble nearby. The marble curves toward the bowling ball, not because the bowling ball is reaching out and pulling it, but because the surface beneath it has changed shape. Einstein realized the universe behaves in much the same way. Stars, galaxies, even black holes don't simply move through space. They reshape it. Light, despite having no mass, must follow those curves. That means an extremely massive object can actually bend light traveling behind it. For decades, this remained one of Einstein's most extraordinary predictions. Then astronomers finally observed it. Entire galaxies appeared stretched into glowing arcs. Others appeared twice, sometimes 4 times. In rare cases, a single distant galaxy formed a nearly perfect circle of light around a massive foreground object. These breathtaking structures became known as Einstein rings. They're not optical illusions. They're gravity itself, made visible. Imagine holding a wine glass in front of a distant streetlight. The glass bends and distorts the light behind it. Now replace the wine glass with an entire galaxy cluster. Replace the streetlight with another galaxy 13 billion light-years away. The result is gravitational lensing, and James Webb is better at seeing it than any telescope before it. The first deep-field image Webb released wasn't just remarkable because it contained thousands of galaxies. It was remarkable because some of those galaxies should have been invisible. Without gravitational lensing, their ancient light would have been far too faint to detect. Instead, a massive cluster of galaxies in the foreground acted like a gigantic natural magnifying glass. Its gravity bent and amplified the light coming from objects even farther away. The universe, quite literally, became its own telescope. That single effect changed everything. Because every time Webb points toward one of these enormous galaxy clusters, astronomers gain a chance to look even farther back in time. It's almost like stacking 2 telescopes together, one built by humanity, the other built by gravity itself. Some of the galaxies Webb has observed owe their visibility entirely to this cosmic coincidence. Without those natural lenses, their light would simply disappear into the darkness. But gravitational lensing offers something even more valuable than magnification. It allows astronomers to weigh the invisible. Remember dark matter? We still don't know what it's made of, but we know gravity bends light. So if astronomers carefully measure how much a background galaxy has been distorted, they can calculate how much mass must exist in the foreground. Sometimes, the visible galaxies aren't heavy enough to explain the distortion. Something else is contributing. Something invisible. Over and over again, those calculations point toward enormous halos of dark matter surrounding galaxy clusters. It's one of the strongest pieces of evidence we have that dark matter is real, not because we can see it, but because gravity reveals its fingerprints. Think of it like walking across fresh snow after someone invisible has already passed through. You never see the traveler, but the footprints leave no doubt that something was there. Gravitational lensing is the universe's footprint, and Webb is reading it in astonishing detail. One of its most famous targets is a galaxy cluster known as SMACS 0723. At first glance, it looks like a beautiful collection of galaxies. Look closer, and something strange appears. Curved streaks of light wrap around the cluster. Some resemble glowing commas. Others stretch into impossibly thin arcs. Those aren't damaged photographs. They're galaxies hiding billions of light-years behind the cluster. Their light has been twisted into extraordinary shapes during its journey to Earth. Some of that light began traveling toward us before our own galaxy had fully formed. By the time it reached the foreground cluster, its path bent around enormous concentrations of mass. Only then, after another several billion years of travel, did it finally arrive at Webb's golden mirrors. Every distorted arc in that image represents an incredible story. A photon left a distant galaxy when the universe was still young. It crossed intergalactic space for billions of years, passed through a natural gravitational lens, changed direction without ever stopping, continued traveling, and eventually ended its journey inside a telescope built by a civilization that didn't even exist when the photon began its voyage. It's one of the most astonishing chains of events in all of science. Yet the deeper astronomers studied these gravitational lenses, the more surprises emerged. Some distant galaxies appeared multiple times in the same image, not because there were several galaxies, because gravity had created multiple paths for their light. Imagine standing in a hall of mirrors. One person suddenly appears 3 or 4 or even 5 times. The reflections arrive from different directions. That's essentially what Webb observes on a cosmic scale. But unlike mirrors, gravity introduces something even stranger: time. Light traveling along one curved path may take longer to reach Earth than light following another. That means 2 images of the same galaxy can actually show it at slightly different moments in its history. Think about that for a second. A single photograph can contain multiple versions of the same galaxy, captured at different points in time. It's one of the closest things nature provides to a real time machine. Astronomers use these time delays to measure the expansion of the universe with extraordinary precision. They compare when light arrives, how far each path traveled, and how gravity shaped its journey. Every measurement becomes another clue in one of cosmology's greatest mysteries. How fast is the universe really expanding? For years, the answer seemed straightforward. Different methods should all produce nearly identical numbers. Instead, they don't. One technique gives one value, another gives something noticeably different. The disagreement is now so persistent that astronomers have given it a name: the Hubble tension. At first, many believed it would disappear as measurements improved. Instead, James Webb has made those measurements even more precise. And rather than making the tension go away, the telescope has strengthened the case that the discrepancy is real. Somewhere, hidden inside the mathematics describing our universe, something may still be missing. Whether that's new physics, an incomplete understanding of dark energy, or something no one has yet imagined, remains one of the biggest unanswered questions in astronomy. And as Webb continued pushing deeper into cosmic history, it stumbled onto another mystery that may be connected. Not a galaxy, not a black hole, not even a cluster of stars, but light that had traveled farther than almost any ever detected. Light from a time when the universe itself was only beginning to emerge from darkness. Because beyond the great galaxies, beyond the brilliant quasars, and beyond the cosmic lenses, Webb was approaching something astronomers have spent decades searching for. The moment the universe first turned the lights on. Part 11. The day the universe turned the lights on. There was a time when the universe had stars, but almost no one would have been able to see them. That sounds impossible. After all, what's the point of a star if its light can't travel? But the early universe wasn't empty. It was filled with something that acted almost like an enormous cosmic fog. To understand why, we have to go back to a time long before galaxies looked anything like they do today. Immediately after the Big Bang, the universe was unimaginably hot. Matter couldn't settle down. Electrons and atomic nuclei rushed through space at incredible speeds, constantly colliding with one another. Light couldn't travel very far before smashing into another free electron. Imagine trying to drive through a city during the world's worst traffic jam. You move a few meters, then stop. Move again, then stop. That was the universe. Photons were trapped. Only after hundreds of thousands of years did the cosmos cool enough for electrons to combine with atomic nuclei, forming the first neutral hydrogen atoms. Suddenly, light could travel freely. That ancient glow still fills the universe today. We call it the cosmic microwave background. It's the oldest light humanity has ever directly observed. But after that brilliant flash, something unexpected happened. The universe went quiet. For millions of years, there were still no stars, no galaxies, just vast oceans of neutral hydrogen drifting through space. Eventually, gravity began gathering that gas into the first stars. Those stars ignited one by one, like distant campfires across an endless wilderness. But there was still a problem. Neutral hydrogen is remarkably good at absorbing certain wavelengths of ultraviolet light. Every newborn star found itself surrounded by an enormous cocoon of gas. Its light couldn't travel very far. Imagine lighting a powerful flashlight inside an incredibly dense fog. The flashlight works perfectly, but from a distance, its beam quickly disappears. Now imagine thousands, then millions, then billions of flashlights gradually turning on across the landscape. Eventually, the fog begins disappearing. That is essentially what happened to the universe. Astronomers call this extraordinary transformation the epoch of reionization. It's one of the most important transitions in cosmic history. As the first generations of stars and galaxies formed, their intense ultraviolet radiation slowly stripped electrons away from neutral hydrogen. The fog began clearing, bubble by bubble, galaxy by galaxy, until finally, light could once again travel enormous distances across the cosmos. Without this event, the universe we know today could never have formed. James Webb was built specifically to investigate this forgotten era. Not because it can photograph the fog directly, but because it can observe the galaxies responsible for clearing it. Every extremely distant galaxy Webb discovers becomes another clue, another flashlight shining through the ancient darkness. By measuring how much hydrogen still surrounded these galaxies, astronomers can reconstruct when different regions of the universe became transparent. It's almost like arriving after a massive forest fire. The flames are gone. But by studying the burned landscape, you can reconstruct how the fire spread. Webb is doing something remarkably similar, except the landscape spans billions of light years, and the fire was the birth of visible cosmic structure itself. One of the biggest questions scientists hoped Webb would answer was surprisingly simple. Who turned the lights on? Was it countless small galaxies? A handful of enormous ones? Powerful quasars? Or some combination of all three? The answer appears to be complicated. Webb has discovered that even relatively small galaxies in the early universe may have played a much larger role than astronomers expected. Although individually faint, they existed in staggering numbers. Together, their combined radiation may have been enough to gradually ionize enormous regions of space. Imagine trying to illuminate an entire city. One giant floodlight would help. But so would millions of tiny light bulbs. Sometimes, the small lights win simply because there are so many of them. If this interpretation is correct, then the universe wasn't transformed by a few spectacular objects. It was changed by countless modest galaxies quietly working together over hundreds of millions of years. It's a beautiful idea, one of the greatest transitions in cosmic history, driven not by a single cosmic giant, but by billions of ordinary galaxies. Yet Webb also found evidence that some massive galaxies and active black holes contributed far more than previously believed. Once again, the universe refused to give a simple answer. Instead, it appears that many different kinds of objects participated in ending the cosmic dark ages. Stars, galaxies, quasars, perhaps all working together. As more Webb observations arrive, that picture continues to become clearer. But while astronomers were reconstructing the universe's first sunrise, they noticed something even stranger. Some galaxies weren't merely visible. They appeared unexpectedly mature. Their stars seemed older than expected, their structures more organized, their chemistry more evolved, almost as though parts of the universe had raced ahead while others were only beginning to wake up. Imagine watching dawn spread across Earth from space. Some cities begin glowing long before others. Entire regions remain dark while neighboring areas burst into light. The early universe may have behaved in much the same way. Reionization wasn't a single event. It happened unevenly. Different cosmic neighborhoods woke up at different times. Webb is beginning to map that process in extraordinary detail. Every new observation adds another piece to one of the largest puzzles ever assembled. But perhaps the most astonishing realization is this. Everything we've explored so far, the impossible galaxies, the ancient quasars, the first stars, the end of the cosmic dark ages, all of it, occurred within just the first billion years of a universe that is now nearly 14 billion years old. If the universe's history were a 2-hour movie, everything we've covered so far would happen in the opening 8 or 9 minutes. The remaining hour and 50 minutes contains everything else. The birth of galaxies like our own, the formation of the sun, the creation of Earth, the rise of life, human civilization. It all comes later, which raises a fascinating question. If so much happened so quickly, what else has been hiding in those first few 100 million years that we simply haven't recognized yet? Because as Webb continued surveying the deepest reaches of space, it began detecting another population of ancient objects, tiny, extremely compact, and so distant that some astronomers believe they may represent one of the missing links between the universe's first stars and its first supermassive black holes. What James Webb found next wasn't just another galaxy. It may have been the bridge between the first light and the first cosmic monsters. Part 12. Did black holes come first? For almost everything in the universe, there seems to be a natural order. Clouds become stars. Stars create galaxies. Galaxies grow black holes. It's the sequence astronomers have accepted for decades. One step leading naturally to the next. Like planting a seed, watching it become a tree, and eventually seeing birds build nests inside its branches. The tree comes first. The nest comes later. At least, that's how it was supposed to work. But James Webb has uncovered several ancient galaxies where that familiar order appears, backwards. Instead of finding small black holes quietly growing inside young galaxies, astronomers are finding galaxies whose central black holes already seem astonishingly mature. It's almost as if the nest appeared before the tree had finished growing. That single possibility has opened one of the biggest debates in modern cosmology. What if, at least in some parts of the early universe, black holes weren't the end of the story? What if they were the beginning? Imagine standing on top of a hill during a rainstorm. Water naturally flows toward the lowest point. Soon, small streams begin forming. Eventually, those streams carve valleys into the landscape. The valleys didn't create the water, but once they existed, they determined where the water would go. Some astronomers now wonder whether the earliest supermassive black holes played a similar role. Their gravity may have acted like enormous cosmic valleys, drawing vast rivers of gas toward themselves. As fresh hydrogen poured inward, the gas cooled, collapsed, and ignited into stars. Instead of galaxies creating black holes, rapidly growing black holes may have accelerated the birth of galaxies around them. It's a remarkable reversal, one that nobody expected James Webb to force us to consider. Of course, not everyone agrees. Science rarely moves in a straight line. Many researchers argue that these early black holes simply grew much faster than expected after their host galaxies had already begun forming. Others believe we're still underestimating how efficiently the first galaxies converted gas into stars, and both ideas remain entirely plausible. That's what makes this moment in astronomy so exciting. We're not watching settled facts being rewritten. We're watching new evidence push scientists toward better questions. Every Webb observation becomes another clue. Every new spectrum, another piece of a puzzle that's still missing half its edges. Then came an observation that made the mystery even more compelling. Using Webb's exquisite infrared sensitivity, astronomers identified galaxies whose central regions appeared unusually bright, even though the surrounding galaxies were relatively small. One explanation is intense star formation. Another is that actively feeding black holes were already dominating the energy output of those young systems. In some cases, it's probably a combination of both. Imagine flying over a city at night. Most neighborhoods glow softly. Then suddenly, one district shines so brightly that it overwhelms everything around it. From miles away, your eyes are drawn to that single point. That's what some of these ancient galaxies resemble. A brilliant heart inside an unexpectedly young body. And if those brilliant hearts truly are rapidly growing black holes, then they may represent the missing bridge between the universe's first stars and the gigantic quasars we explored earlier. The timeline begins to make more sense. First, massive stars form. Some collapse into black holes. Those black holes find themselves surrounded by enormous reservoirs of pristine hydrogen. The young universe is dense. Galaxies lie much closer together than they do today. Gas streams through invisible filaments of dark matter, like rivers flowing across a continent. Everywhere, a young black hole waits. Fresh material keeps arriving. It feeds. It grows. Its gravity strengthens. More gas falls inward. More stars ignite nearby. A feedback loop begins. Not a quiet process, but an extraordinarily violent one. It's difficult to imagine just how energetic those environments were. Modern galaxies often spend millions of years between major collisions. The early universe didn't have that luxury. Everything was closer together. Interactions happened more frequently. Entire galaxies brushed past one another, merged, and reshaped themselves in ways we rarely witness today. The first billion years may have been the busiest construction period in the history of the cosmos. Stars exploding, black holes feeding, galaxies colliding, new structures emerging almost everywhere. James Webb has given us front-row seats to that extraordinary era. And yet, for every answer it provides, another mystery appears. Because while astronomers were debating whether black holes helped build galaxies, Webb quietly turned its attention somewhere completely different, not toward another ancient galaxy, but toward worlds, real planets. Some larger than Jupiter, others smaller than Neptune, worlds orbiting distant stars, whose atmospheres contained chemistry unlike anything found in our own solar system. Some were so hot, their daysides could melt rock. Others drifted through space with no parent star at all. Rogue planets, wandering the galaxy in complete darkness. If the earliest universe showed us how galaxies were born, these alien worlds would reveal something equally profound. Just how unimaginably diverse planetary systems can become. Because what James Webb discovered inside the atmospheres of these distant worlds proved that the universe still had entirely new kinds of planets waiting to be found, and some of them looked nothing like the worlds we grew up imagining. Part 13. Worlds that shouldn't exist. For thousands of years, every planet humanity knew shared one thing in common. They all belonged to us. Mercury. Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Our understanding of planets came entirely from 8 familiar worlds orbiting one ordinary star. Then, everything changed. In 1995, astronomers confirmed the first planet orbiting a sun-like star beyond our solar system, an exoplanet. At the time, finding one seemed extraordinary. Today, we know of thousands. Some are larger than Jupiter, others smaller than Earth. Some complete an entire orbit in just a few hours. Others take centuries. Every year, the universe becomes stranger, and James Webb has taken that mystery to an entirely new level. Unlike previous telescopes, Webb doesn't just detect distant planets, it studies them, not by taking photographs. They're far too distant for that. Instead, it examines something almost impossibly delicate, the tiny fraction of starlight passing through a planet's atmosphere. Imagine watching someone walk in front of a spotlight. For a brief moment, the light changes. Now imagine trying to determine what that person is wearing, not by looking at them, but by measuring how the color of the spotlight changes by less than 1%. That's essentially what Webb does. As an exoplanet passes in front of its star, a small amount of starlight filters through its atmosphere. Different molecules absorb different wavelengths. Water leaves one signature, carbon dioxide another, methane another. Those chemical fingerprints reveal what an atmosphere is made of, without ever seeing the planet directly. It's one of the greatest technological achievements in modern astronomy, and almost immediately, Webb began finding surprises. One of the first worlds it examined was WASP 39b, a giant gas planet roughly the size of Saturn. But unlike Saturn, this world circles its star in just over 4 Earth days. It orbits so closely that temperatures climb to nearly 900 degrees Celsius, hot enough to soften many metals. Webb detected something scientists had hoped to find for years: carbon dioxide. For the first time, this molecule was measured so clearly in the atmosphere of an exoplanet. That might not sound revolutionary. After all, Earth has carbon dioxide, Mars has it, Venus is filled with it. But the significance wasn't the molecule itself, it was Webb's precision. The telescope wasn't merely detecting an atmosphere, it was reading its chemistry from hundreds of light years away, almost as though it were performing laboratory analysis across interstellar space. Then came another discovery: sulfur dioxide. Unlike carbon dioxide, this molecule isn't simply sitting inside the atmosphere. It forms through chemical reactions driven by energetic starlight. In other words, Webb wasn't just observing a distant atmosphere, it was watching atmospheric chemistry unfold in real time. That was something entirely new. It proved Webb could detect active weather, active chemistry, and the influence of alien sunlight on worlds humanity will probably never visit. Suddenly, exoplanets stopped feeling like distant dots on a graph. They became real places, places with skies, clouds, winds, chemical cycles, entire climates unlike anything in our own solar system. And that realization opened the door to an even bigger question. If Webb could detect carbon dioxide, what else could it find? The answer came from another remarkable world, K2-18b. Located about 120 light-years from Earth, this planet is far larger than our own, neither a rocky Earth nor a gas giant like Jupiter. Instead, it belongs to a mysterious class astronomers call sub-Neptunes, worlds that don't exist anywhere in our own solar system. That alone makes K2-18b fascinating. But Webb's observations made it famous. The telescope detected strong evidence for methane and carbon dioxide in its atmosphere. Those molecules are consistent with a hydrogen-rich atmosphere surrounding a planet that may contain enormous quantities of water beneath. Some researchers have proposed that K2-18b could belong to a hypothetical class of worlds called Hycean planets. Imagine an ocean stretching across an entire planet, covered by a thick, hydrogen-rich atmosphere. No continents. No mountain ranges. Just a global sea beneath an alien sky. It's an intriguing idea, but it's important to be careful. At the moment, it's still only one possible interpretation of the data. Webb has revealed the atmospheric chemistry. Exactly what lies beneath those clouds remains uncertain. That's the difference between observation and interpretation, and astronomy advances by keeping those two things separate. Even so, K218b demonstrated something profound. The diversity of planets in our galaxy is far greater than anyone imagined a generation ago. Our solar system, once thought to be the template for planetary systems everywhere, may actually be just one variation among billions. Then Webb turned its attention toward one of the most extreme planets ever discovered, a world called 55 Cancri E. If Earth is a comfortable home, 55 Cancri E is a furnace. It orbits so close to its star that 1 year lasts less than 18 hours. Stand on its day side, and temperatures soar above 2,000 degrees Celsius, hot enough to melt iron, hot enough to keep entire oceans of lava in a molten state. For years, astronomers couldn't agree on what this world actually looked like. Some imagined a bare rock, its surface scorched clean by stellar radiation. Others proposed a deep global ocean of magma. James Webb added another piece to the puzzle. By measuring heat coming from both the day side and the night side, the telescope found evidence suggesting the planet may possess a substantial atmosphere. That's remarkable. A world this close to its star should struggle to hold on to any atmosphere at all. Intense radiation constantly blasts away gas. Yet somehow, something appears to remain. Perhaps volcanic activity continuously replenishes it. Perhaps the atmosphere is richer in carbon compounds than expected. Scientists are still investigating, but Webb once again revealed that planets are capable of surviving under conditions far more extreme than we once believed. Then, it found something that wasn't orbiting a star at all. A planet, completely alone, drifting through interstellar space. No sunrise, no sunset, no parent star warming its skies. Just endless darkness. These are known as rogue planets. Most likely, they formed inside ordinary planetary systems before violent gravitational interactions flung them into deep space. Imagine spending billions of years orbiting a peaceful star, only to be hurled into the void forever. No light, no warmth, only the faint heat trapped deep inside your own interior. For decades, astronomers wondered how common these lonely worlds might be. James Webb helped provide part of the answer. While studying the Orion Nebula, the telescope identified hundreds of free-floating planetary mass objects. Some appeared isolated, others seemed to travel in pairs. These strange paired objects are still being studied, and astronomers are debating exactly how they formed. They challenge traditional ideas about both planet formation and star formation. Some may truly be planets. Others may instead be extremely low-mass objects formed more like stars. Either way, they reveal that nature is more creative than our categories. The universe doesn't care whether something neatly fits inside our textbooks. It simply exists. And James Webb continues showing us that reality is often far more imaginative than our theories. But as astonishing as these alien worlds were, they weren't what Webb had been built to find. Its greatest mission still lay ahead. Beyond every galaxy, beyond every quasar, beyond every planet, there remained one final frontier, the edge of the observable universe itself. And what James Webb discovered there would leave astronomers asking one final question. Not, what are we looking at? But something far more profound. Have we finally reached the beginning, or is there still something waiting beyond? Part 14. The Edge of the Observable Universe. No matter how powerful our telescopes become, there is one place they can never reach. Not because the technology doesn't exist, Not because the light is too faint, because the universe itself has drawn a boundary. Imagine standing on a beach at sunset. The ocean stretches endlessly toward the horizon. No matter how far you walk, the horizon always remains ahead of you. It isn't a physical wall. It's simply the limit of what you can see from where you stand. The observable universe works in much the same way. Every telescope, from Galileo's tiny refractor to the James Webb Space Telescope, is limited by one simple fact: light travels at a finite speed. When you look at the moon, you're seeing it as it was about 1 second ago. Look at the sun, and you're seeing it roughly 8 minutes in the past. The Andromeda Galaxy? Over 2 million years ago. Every step outward is another step backward through time. James Webb has pushed that journey farther than any telescope in history. Some of the light reaching its mirrors has traveled for more than 13 billion years. Those photons began their journey before Earth existed, before the sun ignited, before our galaxy settled into its familiar spiral. But eventually, even Webb reaches a limit. Not because the telescope isn't powerful enough, because there comes a point where no visible light yet exists. Before the first stars, before the first galaxies, there was nothing to illuminate the darkness. It's like opening a history book. You can keep turning pages backward. Ancient civilizations, the first cities, the first farmers, the first humans. Eventually, the pages simply end. Not because history stopped existing, because there were no writers yet. The universe has a similar boundary. Beyond the first stars, there are no galaxies to photograph. Only darkness. Not empty darkness. Just a universe waiting for its first lights to ignite. This is why astronomers often describe Webb as a telescope that looks through time. It isn't simply observing distant objects. It's reconstructing history. Every galaxy, every spectrum, every tiny red smudge becomes another sentence in a story that began nearly 14 billion years ago. And yet, there is a profound misconception about the phrase, the edge of the universe. Many people imagine a gigantic wall, a final boundary, a place where space simply ends. Reality is stranger. The observable universe isn't the entire universe. It's only the portion whose light has had enough time to reach us since the Big Bang. Imagine standing inside an enormous forest during a thick fog. You can only see a short distance in every direction. That doesn't mean the forest ends where your vision stops. It simply means the light from farther away hasn't reached your eyes. The observable universe is our cosmic visibility limit. Beyond it, space almost certainly continues. Perhaps forever, perhaps not. We simply don't know. Current observations suggest the universe is at least hundreds of times larger than the observable region. It may even be infinite. If that's true, then everything humanity has ever observed, every galaxy, every black hole, every nebula, every star, occupies only a tiny fraction of reality. It's a humbling thought. Imagine removing a single grain of sand from every beach on Earth. Now imagine trying to describe the entire planet using only that grain. That's roughly how small our observable region could be compared to the whole. James Webb wasn't built to answer whether the universe is infinite. No telescope can. But it has done something equally remarkable. It has shown us that the earliest observable universe was already astonishingly rich. Galaxies, stars, black holes, chemical elements, all appearing earlier than many expected. That realization changes the way astronomers think about cosmic history. Instead of asking, when did galaxies begin? Researchers now ask, how did they begin so quickly? Instead of, when did supermassive black holes appear? They ask, what process allowed them to grow so rapidly? The questions themselves have evolved. That's one of science's greatest strengths. Every discovery replaces old mysteries with better ones. Then Webb uncovered something almost poetic. The farther away a galaxy lies, the more the universe stretches its light. Eventually, visible light becomes infrared. Push even farther, and that light stretches beyond Webb's detectors. Not because the galaxy disappears, because the wavelength itself becomes too long to measure. It's as though the oldest light in existence is slowly whispering instead of shouting. The message is still there. We simply need new instruments to hear it. That's why the James Webb Space Telescope isn't the end of this story. It's the beginning of another. Astronomers are already imagining observatories even larger, even colder, even more sensitive. Telescopes that may one day detect the first generation of stars directly, or perhaps find galaxies even older than those Webb has revealed. Every generation of astronomers believes they are approaching the final frontier. Then technology advances. The frontier moves again. History has repeated that lesson for 4 centuries. It will almost certainly repeat it again, because the universe has a habit of being larger than our imagination. And James Webb has reminded us of that better than any telescope before it. But among all the discoveries Webb has made, there is one lesson that stands above the rest. It isn't about galaxies, or black holes, or alien worlds. It's about us, because every atom in your body, every breath you've ever taken, every thought you've ever had, can trace its origins back to the very events Webb is now witnessing. The first stars, the first explosions, the first galaxies. Without them, none of us would exist. Which means this journey to the edge of the observable universe has quietly become a journey back to our own beginning. And that's what makes Webb's greatest discovery far more personal than anyone expected. Part 15. The universe was never what we thought. When this journey began, we believed we were traveling to the edge of the universe. What we found instead was the edge of our understanding. For thousands of years, humanity believed the night sky was simple, a handful of stars, a few wandering planets, and a dark emptiness surrounding them. Then the telescope was invented. Suddenly, the universe became larger. Galaxies replaced stars as the building blocks of the cosmos. Then we discovered there wasn't just one galaxy, but trillions. Then we realized those galaxies were moving away from one another. Then we discovered black holes, dark matter, dark energy, exoplanets. Every generation believed it had almost finished the puzzle. Every generation was wrong. James Webb has continued that tradition, not by proving that everything we knew was false, but by revealing how much of the story was still missing. Think back to everything we've seen. Galaxies that appeared far earlier than expected. Ancient star factories producing suns at astonishing rates. Supermassive black holes already feeding when the universe was still in its infancy. Alien worlds with atmospheres unlike anything in our solar system. Gravitational lenses bending light across billions of years. The first hints of how darkness itself gave way to starlight. None of these discoveries destroyed modern astronomy. They did something far more valuable. They exposed the places where nature is still ahead of us. Science is often misunderstood. People imagine it as a collection of answers. In reality, science is a process for discovering better questions. Every time James Webb observes something unexpected, astronomers don't throw away centuries of knowledge. They investigate, they test, they challenge their own assumptions, they improve the picture. That's why the history of astronomy is one of constant expansion. Not just the expansion of the universe, but the expansion of human understanding. And perhaps that's Webb's greatest achievement. It hasn't simply shown us older galaxies, it's reminded us to remain curious. Because curiosity is what built this telescope in the first place. Imagine trying to explain James Webb to someone living just 200 years ago. A machine unfolding itself 1.5 million kilometers from Earth. Mirrors aligned with nanometer precision, detecting photons that began their journey before our planet existed. They would probably call it impossible. Yet today, it's quietly orbiting the sun, sending humanity a new picture of the universe almost every week. That thought alone says something remarkable about our species. We're small, incredibly small. The Earth is tiny compared to the Sun. The Sun is tiny compared to the Milky Way. The Milky Way is just one galaxy among hundreds of billions inside the observable universe. And the observable universe itself may only be a fraction of everything that exists. By every physical measure, we are insignificant. Yet despite our size, we've managed to understand something extraordinary. Atoms inside our brains, forged in ancient stars, have somehow become capable of asking where those stars came from. The universe has produced creatures that can study the universe itself. Perhaps that's one of the rarest events in all of cosmic history. The iron flowing through your blood was created inside a dying star billions of years ago. The oxygen you breathe was forged in stellar furnaces long before the sun existed. The calcium in your bones, the carbon in every cell, the gold inside your electronics. All of it was manufactured in explosions that James Webb is helping us understand. When you look into the night sky, you are not looking at something separate from yourself. You're looking at your own history. The atoms that built you once drifted through the very galaxies Webb is now observing. In a very real sense, this telescope isn't simply exploring the universe, it's exploring our origin. And that's what makes its discoveries so deeply human. Because every answer Webb provides eventually leads back to us. Where did the first stars come from? How did galaxies assemble? Why do black holes grow? How did the chemical elements spread across the cosmos? Every question ultimately becomes another chapter in the story of how a lifeless universe eventually produced planets, oceans, life, and consciousness. Yet perhaps the most humbling lesson of all is how much remains unknown. We still don't know what dark matter is. We still don't understand dark energy. We still don't know exactly how the first supermassive black holes formed. We still don't know whether the universe is finite or infinite, or whether our observable universe is only one small part of a much larger reality. Those aren't failures, they're invitations. History suggests that whenever humanity reaches what feels like the edge of knowledge, another horizon appears. James Webb has taken us farther than any telescope ever built. One day, another observatory will go farther still. Perhaps it will detect the very first stars directly. Perhaps it will discover the earliest galaxies ever formed. Perhaps it will answer questions we haven't even thought to ask yet. And one day, future generations may look back at James Webb the same way we look back at Galileo's first telescope, not as the end of exploration, but as the beginning of a completely new era. Because that's the remarkable thing about the universe. Every time we think we've reached the end of the story, it quietly turns another page. Maybe that's why the night sky has fascinated humanity for so long. Not because it gives us certainty, but because it refuses to. Every star, every galaxy, every ancient photon crossing billions of light years is a reminder that reality is larger than our imagination, and perhaps it always will be. The edge of the universe wasn't a destination, it was a mirror. The farther James Webb looked into space, the farther it looked back in time. And the farther it looked back in time, the closer it came to answering the oldest question humanity has ever asked. Where did we come from? For now, the universe has given us another piece of the answer, but not the final one, because somewhere beyond the most distant galaxy James Webb can see, beyond the oldest light ever detected, beyond the horizon itself, the next mystery is already waiting, and someday we'll build another telescope, look a little farther, and discover that the universe is even stranger than we imagined. Thank you for watching.